So in this video, we're going to review some basic concepts of polynomials. So a polynomial consists of one or more terms that are linked by addition. And remember, when I say addition, that does include subtraction, as subtraction is really just a sort of a special case of addition. Terms are created as a product of a real number. That real number could be 1, in which case we don't usually write it, with one or more variables with positive integral powers. So a monomial is another word for a single term. A polynomial that is just one term could be something like 4x cubed. So that's a real number, 4, with a positive integral power of x. You could have something like x cubed y to the power of 2. That's a monomial that has a real number is 1, so we don't bother writing it. And then x and y both have positive integral powers. A monomial could just be something like x or a or b or whatever variable, or it could actually just be a number. So 53 could be considered a monomial. It is something that could be a term appearing in a polynomial. Now, ordinarily, if all you have is 53, you're not going to call that a polynomial. But if we're in the context of working with a bunch of polynomials, 53 can be treated as a polynomial. It's a monomial with basically no variables. The power of the variables would be considered to be 0. A binomial would then have 2 of these terms. So let's say, for example, 4x cubed minus x. That would be a binomial. Or we could have something like just a plus 7. Or we could have 3y squared minus 2x squared. These would all be considered binomials, where the individual terms are linked by an addition or by a subtraction. I could consider this last one, for example, where I've got subtraction, could be considered the addition of 3y squared plus negative 2x squared. That's why it counts under this definition. And a trinomial would have 3 terms. So you could have something like 3x squared minus 2x plus 7. That's a very common type of trinomial that we'll see called a quadratic. We'll talk about that word in a minute. You could have just a plus b plus c, for example. These are examples of trinomials. There are names for polynomials with 4 or 5 or 6 terms. We don't need to bother knowing those names. So you could just say a 4-term polynomial. Technically, well, there are names, but they're kind of pointless to memorize past a point. The coefficient is the real number factor of the term. So for example, in this first monomial, 4 is the coefficient. Here, I would consider negative 2 to be the coefficient. And the principal coefficient of a polynomial is the coefficient of the term with the highest degree. That's the highest power. So in this trinomial here, 3 would be the principal coefficient. In the binomial here, 4 would be the principal coefficient. In this one, 1 is the principal coefficient. And actually here we don't have a principal coefficient in this last binomial because they both have the same power. Degree relates to powers, so it relates to exponents. The degree of a specific term is the sum of all the powers of the variables. So if I come back to these examples I did here, the degree of this monomial is 3. The degree of this monomial is 5 because I have a power of 3 and a power of 2. The degree of this monomial is just 1, and the degree of this monomial is 0. Individual terms have degrees, so this would be a term of degree 3, this would be a term of degree 1. Here in this first trinomial, we have a term of degree 2, a term of degree 1, and a term of degree 0. So we can name the degree of each individual term, and we have specific names for some of these powers. So constant would be something that has a degree of 0. So if we understand, look at the examples here that had constants. So these were all degree 0, the 53, and then the a plus 7. The 7 is a constant. And 3x squared minus 2x plus 7. The 7 is again a constant. Constant is the opposite of variable. They are constant because they do not have any variables, so that will always be worth 7, or it will always be worth 53, regardless of what value x takes. So those are degree 0. The linear terms are the terms with degree 1. The quadratic terms are the terms with degree 2. And the cubic terms have degree 3. Again, there are names for powers of 4 and powers of 5, but we don't need to know them. You can just say that is degree 4, that is degree 7. And then the overall polynomial has the degree of its highest term. So in the case of this first trinomial, the overall trinomial is degree 2. And in the case of this first binomial, the overall degree here is degree 3. Because the highest term, the highest power term, not necessarily the first, although I have written these in order of highest power to lowest power, the highest power of a term is the power of the binomial, or the polynomial, sorry. All right, when simplifying polynomials, for addition and subtraction, I combine like terms. And so in this case, I'm going to essentially, because all I have here is addition, I can ignore the brackets because addition is associative, and I can change the order because addition is also commutative. So I'm going to treat this as x squared plus 3x squared plus 2x plus 5 plus 9. Then I can obviously add the 5 and the 9 together. These two I can add together by essentially using the factoring out a common factor. So x squared is common here. If I divide both of those terms by x squared, I'm left with 1 plus 3. Now I'm writing more steps here than I would normally write, but this would then simplify to 4x squared plus 2x plus 14. I can do the same for subtraction, but I do have to remember that subtraction needs to be distributed to the brackets that come after it. So in other words, this subtraction in front of the parentheses turns the whole, or changes the sign of every term inside. So to turn it into an addition, I have to be adding the opposite of every term inside those brackets. So this becomes minus 2x squared minus x plus 10. Now I can group together the like terms. I only have one cubic term, so 3x cubed. Quadratic terms, I have minus x squared and minus 2x squared, which means I have minus 3x squared. Linear terms, I have plus 5x minus x, which leaves me with plus 4x. And then constant terms, I have minus 3 plus 10, which leaves me with plus 7. So this is the simplified polynomial. Multiplication is a little more complicated. Multiplication requires us to distribute every term in the first polynomial times every term in the second. And I'm going to actually show this 3 different ways to show 3 different ways we can organize and make sure we get all the multiplications. First, I can sort of organize it like I would if I were multiplying just numbers together. So I can stack them vertically like this. And then I multiply everything times the 7. So 3 times 7 is 21. 9 is positive 21, so I'm going to put a plus. 9x times 7 is 63x. And x squared times 7 is 7x squared. I don't have to worry about carrying digits, so in that way this is nicer than when I'm multiplying with numbers. But now I'm going to multiply everything in the first trinomial times the 2x squared. But I'm going to respect place value essentially, so I'm respecting degree. So when I multiply 3 times 2x squared, I get 6x squared. I'm going to write that with the 7x squared. 9x times 2x squared is 18x cubed, and x squared times 2x squared is 4x to the power of 4. When I then add these together, I've lined up the like terms, so I end up with 4x to the power of 4 plus 18x cubed plus 13x squared, because I have 7x squared and 6x squared, plus 63x plus 21. Another way to organize this is using boxes. So I'm going to consider that I have a 3 times 2. So x squared, 9x, and 3 are my trinomial terms, and 2x squared and 7 are my binomial terms. So in each box, I'm going to multiply the term at the edge of that column and row. So 2x squared times x squared is 2x to the power of 4. I, for some reason, wrote 4x to the power of 4 over in my previous one, but it is 2x to the power of 4. 2x squared times 9x is 18x cubed. 2x squared times 3 is 6x squared. Then I got 7x squared, 63x, and 21. All the same things I got when I was multiplying the other way around. It's just organized a little differently. Now when I'm adding them together, I'm looking for the two that are like terms. That would be these two. And I end up with exactly what I ended up with before. I should. These are just different ways of showing the same multiplication. So 2x to the power 4 plus 18x cubed plus 13x squared plus 63x plus 21. I'm not going to fully do the other multiplication, but essentially what I would do is I would organize it horizontally. So I usually do bother drawing this bar. So I would draw that bar and write that multiplication. Then I would do this one. Then I would do this one, and then this one, and then this one, and then this one. That can get a little messy, but as you get more comfortable, or if you're multiplying things that only have, say, a binomial times a binomial, where you don't have nearly as many multiplications to do, this might be the quickest way for you. All right, so now here's something of an application of polynomials. So let's say we have a rectangular garden that's 5 meters wider than it is long. With these types of questions, I often will draw a diagram. So I have a rectangle. It's 5 meters wider than it is long. So I'm going to call this the length. And this will be 5 meters more than that. Find simplified expressions for its perimeter and area. So for the perimeter of the rectangle is the sum of all four sides. So L plus L plus L plus 5 plus L plus 5. So the simplified expression here, well, I have 4 L's plus 10. So that's the simplified expression for the perimeter. It is measured in meters, so I can call it meters. And the area, well, area is length times width, so that's going to be L times L plus 5, which involves a distribution. So this is an example where it's probably very efficient just to do your multiplication this way. So L times L is L squared, and L times 5 is 5L. And that is in meters squared because it is area. So there's a simplified expression for the perimeter and a simplified expression for the area.